Good morning, and thank you for that welcome and for that introduction. It's always, for me, it's always a privilege to talk about a topic that I'm really passionate about. And that's the role of agricultural biotechnology in development. I understand that I'm speaking to a mixed audience with varying levels of technical expertise, so the topic of today is more of a type of message that can be delivered to general audiences as opposed to giving a formal research seminar. So when we started talking about biotechnology, or more specifically GMOs, it's been a controversial topic since the beginning. And those that have heard me talk before know that I like to start with a cover of Greenpeace magazine. Because way back to 1999, and they're trying to tell us that we have dangerous technologies there. So dangerous a guy has to use his gown and goggles and mask and forgot gloves. So from the beginning, we have not had an honest message. When I'm on campus, though, I have 25 years of research on genetic engineering, the use of engineered crops, how to make them, how to use them. But my teaching is actually in a campus that we have in Central America, and it's agroecology. Now, I've been told by many people that agroecology and sustainable and agriculture and genetic engineering are mutually exclusive. And I'm here to argue just the opposite. Agroecology and a knowledge of the principles behind agroecology inform us as to what are the traits we need to be working on. And the traits we can achieve with engineering really help and make it easier to implement sustainable agricultural systems. I was originally born right about here and grew up in this region, and to this day my main area of work is in Latin America when it comes to biotech regulations and outreach. So one of the really neat things about being in the Philippines, of all the Southeastern Asian countries, it reminds me of home the most. Culturally and with the vegetation and the landscape. One of the projects that we have, and this is we were able to actually coordinate all the environmental risk assessors from the continent, and we wrote a guide for environmental risk assessment of GMOs. It was tailor-made for the Latin American reality. You know, a lot of stuff Europe sends out is just not applicable. And it's in Spanish because that's what most of our regulators speak. And we have a version in Portuguese as well. And on top of that, I have done a lot of work on the food and feed safety assessment of GMOs, which are all in refereed publications. But I'd like to start off then with the topic of genetic modification and what it is. It's something old, very old. And this is a picture I put together many years ago. Because it's been pointed out that the crops that we all use have been so modified that it takes a very well-trained botanist to be able to identify the wild relatives of our crops, what our crops looked like before people got in to modify them. So for those who haven't seen this picture before, what are you looking at? You're very familiar with these crops. Somebody? Speak up, I can't hear.
That's me. Parrott.
That is the very essence of genetic modification. And just remember that it is impossible, barring minor differences with epigenetics, it's impossible to change the way a crop looks without changing the DNA underneath it. And we're just now understanding these changes now that we can sequence genomes. But the point is that we have been changing DNA for many centuries, even though people didn't realize what they were doing at the time. And today, in the past century, genetic modification became a science. It became the science of plant breeding. And because of that, all our crops there's just a tremendous amount of diversity in the way they grow and the way they behave, the color, the taste, and just about any trait you want to think about. And on top of that, not only do we breed for quality and yield, pest resistance is a particularly major problem. This happens to be a soybean leaf from one of our research plots. And one of the graduate students just, was amazed. He came over and said, just realize that this one little section, you take a close look, you got one insect and 3 different diseases. And that's what farmers face in the field every day. Now, most farmers I know rather harvest soybean than harvest mold or insects, so they have 2 choices. They can use chemicals, or they can go to a breeder and ask breeders to develop resistant lines. So what a breeder will do is many times they go to the wild relatives. Again, this happens to be a row of soybean, and this is one of the wild soybeans, and again you can see what it really looked like before it was modified. And the problem in this case is it's susceptible. In this case, it's frog-eye leaf spot. The necessary genes for resistance are coming from the donor here, this wild soybean. It is the job of the breeder to cross the 2 of them together and then spend about 10 years sorting out the bad traits that they don't want for agriculture, the bindiness, the small seeds and whatnot, until he's got all the high quality plus the 1 gene for resistance from the donor. And this has been our bread and butter. This has sustained our agriculture for the past century. The problem starts to come in when there is no resistance in the wild relatives, or the trait you need is not in the wild relatives, at which point they start resorting to genetic engineering. The classic example would be these papayas. They look very, very bad because they're infected with a virus, the papaya ring spot virus, which is it's an epidemic around the world. These happen to be in Thailand. So in a laboratory like mine, or like many laboratories here in the Philippines, we can start cell lines in culture. And then from the cell lines, we add the DNA to them. DNA from just about anywhere. In this particular case, what we need is resistance to the virus. It's cultured. We add hormones to the culture plate to make the callus grow, and by changing the types of hormones, we get the cells to give us small plants, which become big plants. And the only difference then between here and there is 1 gene for resistance. So that's the whole premise behind genetic engineering. So what is genetic modification? For an agronomist and a plant breeder like me, going from the wild relative to the cultivated form and coming up with all the variability that I showed you in the photographing, this process of crossing in desired traits is modification. In the more modern meaning, the way the media, the press, and people use it and think about it, they're really referring to genetic engineering. Other people call it biotechnology. Some people call it transgenic. Or the coin of the realm is GMO. In a lot of legal documents have the word GMO in it, for genetically modified organism. So to put things in perspective, biotechnology is a huge field. It goes across agriculture, it goes across medicine, it goes across food science and preparation. And it's just within it a biotech, and we have a much smaller group of technologies that follow our genetic modification. And under genetic modification, we have an even smaller group that falls under engineering, or GMOs. So the focus of my talk is specifically about the GMO category. So within GMOs, again, we have many things. like vitamin supplements, insulin and other pharmaceuticals, some of the more modern vaccines. They're all the products made with GMO organisms. In this day and age, most beers and wines are made with GMO yeasts. Cheese, the enzyme in practically all the cheese around the world comes from GMO organisms. Artificial sweeteners tend to be GMO. And all of these are used all over the world, and they're never a cause for concern anywhere. It's only when we get to the GMO crops that people start to worry. And even though I don't really see any big difference between the two categories. But my topic for the rest of the day is specifically the GMO crops. So I'm sure all of you have seen a version of this map before. And it is last year, the GMOs were legally planted in these countries that are in the darker green. It includes most of the Western Hemisphere and key parts in Asia, Southeast Asia. It's less common in Europe and less common in Africa. So we started planting GMOs in 2004, even though the records really didn't start until about 2006. And when you look at the adoption of these, in just 17 years, it's gone all the way up to over 170 million hectares. And on top of that, that really makes it the fastest adopted technology in the history of agriculture. The reason this is significant is because if you add up all the land area over these 17 years, we have 1 billion hectares of experience with GMOs. We have experience of 17 years, 1 billion hectares, over 17 million farmers, and about some 30 countries around the world. Which means that when people ask questions about GMOs or express concerns about GMOs, we can actually answer them based on experience, and real-world experience. We don't need to be guessing, and we don't need to be speculating about it. We've got the data to answer the questions. Also, to give you a sense of comparison, this is the growth of the organic industry. The organic industry is probably the second fastest growing sector of agriculture, and by comparison, it really lags behind the GM agriculture. So, one of the big limitations that we have is that there's 160 countries on Earth, and that they're only legal in about 30, which leaves a large section of the population that has no access to GMOs, so they can't experience them firsthand. And even for the countries where they are legal, most of the, about half of the population is in cities now. They don't get out to the country, so they really have never seen a GMO in person, and they really don't know what they're talking about. So what I have done here is taken some of the GMOs that are either commercialized or in the pipeline and divided them in two categories. The category that's coming from the private sector, and then the category that's coming from the public sector. And this is one of them. So not everything has to be about food. These are novel color flowers. They're made by a company in Australia. They're grown in South America, and they're shipped to Europe and Japan. And in Japan particularly, I was talking with the CEO of the company. In Japan, each of these roses brings somewhere between 20 and 30 US dollars. So you can tell it's a wonderful business for them. They also ship them to Europe. The only issue is that if you want to ship them to Europe, you have to label them as not for human consumption, just in case anybody was wondering. But closer to home, where I live in the U.S., We do grow fresh vegetables. We have a window of time, as the spring comes in, they start very south of the U.S. and plant further north as the summer progresses. These are our squash plants. Again, you can see the impact of viruses on the squash, and you can see the GM version. One of the issues was that the virus that infects the plants also really damages the fruit. And how many of you would eat these? Raise your hand. Yeah, the thing is, the irony is they're actually safe to eat. They just don't look good. But there was a lot of waste. A lot of it had to be thrown out because people like you refused to eat them. So now, with the engineered versions, about 90% of the crop is harvestable. Of course, you can see the varieties are sold with this really imposing names: Justice, Conqueror, Liberator. So, the giveaway that near GMO is this 3 underneath it. That's the number of virus resistances that are into it. Another category, though, is herbicide tolerance. The idea is to simplify application of herbicides. This is a photo in Paraguay in South America, just a demonstration plot showing what happens to, this is soybean, if herbicides are not applied. The yield in this half of the plot is going to be probably half of what the yield is on that half, and that's simply due to loss from weeds. Here's another one. This happens to be rice with herbicide tolerance in it. Here you have a mixture of rice and red rice, and you really can't tell them apart, and here you tell them apart very well. One of the things about the private sector, though, is that it's only private as long as a patent is viable, and all patents expire. So the herbicide tolerant soybean, this time next year, it's off patent. It enters the public domain, which means people can save their seed all over the world, not just in Argentina and Brazil. Herbicide tolerance, historically, really about the only reason to justify plowing is to control weeds. Once you have an alternative that's easy to employ, you don't need to plow. This is again in Central America, and all they did there was punch a hole in the ground, drop a seed in, and then kill the weeds with herbicide, leaving the weeds to protect. The dead weeds now are protecting the soil. Central America can get some torrential rains. We can easily get 20, 30 centimeters during a hurricane or in the rainy season. So this is really a big measure towards preventing soil erosion from washing away as much. Another one is insecticides. The resistant crops are called BT crops. And historically, if one had problems, the alternative is you spray. And anything that's underneath that spray is out of luck. Doesn't matter if you're a butterfly, a frog, whatever, you're out of luck. And in many areas, farmers just don't use adequate protection. And I've actually spoken to groups of farmers, and I always will ask, how many of you have ever sprayed using inadequate protection? Nobody raises their hand. Then I can ask, well, how many of you know somebody that sprays without using adequate protection? And then the whole room will raise their hand up. But if you look at the World Health Organization data, it's about 3 or 4 million farmers poison themselves for this reason, and 200,000 or 300,000 of them die every year for this reason. So it's not just an environmental concern, it's a public health concern. Here's one of the first of the insect-tolerant crops was against the bollworm. And here you can see the damage it does in the boll. And you see the engineered version, but at the field level, this is a photograph, again, taken very near where I live. And I think you can tell the engineered half. And when you start seeing photos like this, it becomes very easy to understand why farmers really want that technology. Another problem, corn borers. The North Americans have one, the Latin Americans have one, Africans have one. Here in Asia, there's a different one. And what these do is they enter the stalk and hollow it out. We call that invisible damage because on the outside it looks okay, but on the inside you're losing yield. And not only are you losing yield, the stalk is weakened, and anytime the wind blows or it starts to rain, the inevitable happens. And again, you can tell the engineered half and the non-engineered section there. Armyworms. Particularly in the tropics, they do a lot of damage. And again, here is the very nice ones. You don't see the amount of damage there. And here's again an earworm doing what earworms do to an ear of corn. And it's a major issue for us for a lot of reasons. One is you lose yield. But number two is the wounds that insects make become infected with fungi. And so here you have a GM ear, a GMO, and you have then the conventional. When our smallholder farmers tend to have very low yields to begin with. It's miserable yields, actually, ton and a half per hectare. But which happens to be the same yields that used to be in England during the Roman Empire. Depending on what type of fungus infects it, the fungus can do a lot of toxins. So in areas of China, Africa, Latin America where these toxins exist, we get very high rates of liver cancer and birth defects. And we can have easy ways to control this, and we would just be willing to deploy the technology. And they do eat that. They don't have a choice. You know, that when your yields are low, you eat whatever you can. Here's some of the experiences again with smallholder farmers. Just a farm, you know, again, very low tech. Here's a farmer and his son showing off his GM cob for his conventional cobs. Again, the fungus problem in the conventional and the non-conventional. Or again, an idea of who is impacted by this technology. South African experience has been very much the same. They're getting about a 20% yield increase simply by switching type of corn they plant. It's a brand new product for Latin America. This is the insect-resistant soybean. And again, when the caterpillars move through, they can really do a lot of damage if they're not sprayed. The rootworm resistance. You know, plants have roots for a reason. And here's a healthy root system protected by a transgene. There's one protected by insecticides. And what happens if the root is not protected from damage? And this, you know, you just think about it, if you have any sort of stress, or say a drought stress or what have you, this root will protect the plant a lot better than that root, and you can see that very well. The damage insects make really has affected the ability of the plants to grow when there's a lack of water, in this case. As climates change, one of the predictions is there'll be we're going to be drier in many areas. I know it's hard to believe we're going to be drier given the amount of rain that's out there right now in the past few days. But last year, North America had one of the worst droughts ever. And if you notice the corn, those that had access to engineered corn just managed to get through the drought in much better condition than those that did not. So that's what the private sector is offering. The public sector has not been left behind. And one of the very first products of the public sector was the GM papaya. This is the island of Hawaii, and it was their main agricultural export. And the same virus I showed you from Thailand is attacking their papayas here. And it was just a collaborative effort between Cornell University, the University of Hawaii, and the USDA that led to the papaya that really saved the industry on the island. But this is an effort from the government of Brazil that's done entirely in their Ministry of Agriculture. There, the staple crop for the countryside is beans, dry beans. And it also suffers from viruses. And the reason this plant looks healthier is because it was engineered to resist the virus. But what's really impressive is at the time of yield. You can see the difference. So this is what farmers have had to eat, and here's what the government wants them to have to eat. And they're really investing in this as a way to provide more food security in the countryside. Other products. This is between USAID funded project. A tuber moth resistant potato could be available. Just need to find a country willing to accept it. Projects going on in Africa. Cowpea, the podborer resistant cowpea to prevent that type of damage. And again, specifically designed for smallholders. This is a banana plant in East Africa, actually West Africa. Let's get the impact of bananas and Anthemonas wilt on it. And here are the field trials in East Africa, where you can see how the engineered plant is doing. And by the way, in those parts of Africa, banana are one of their main staples, one of their main sources of calories. The Africans also have the Water Efficient Maize for Africa project, where they're putting in conventional breeding for drought tolerance and adding all the transgenes for insect resistance to do it. And the hope is to get 20-30% yield increase in sub-Saharan Africa, where the problems are the most serious. There's 2 or 3 cassava projects going on with virus resistance. And again, you can see the conventional cassava versus what it could be looking like if you could just eliminate viruses. This is actually from here. Dr. Haltia gave me this photograph to share, but the reason I'm bringing it in is I think you're all aware of the problems in the Philippines, but there's a similar one going on in Bangladesh. And 2 days ago, or 3 days ago now, the Supreme Court of Bangladesh denied Greenpeace request to ban the eggplant, and it has thus cleared the path to release it to the public. I was in India with people there just 2 days ago, and they're really hoping that by December it's becoming available to the public. So that's sort of a taste of what is out there. And since the beginning, or at least in the early days of biotechnology, we used to say it was a scale-neutral technology. That this large holder here, and this guy actually owns everything that you can see in that photograph, was going to benefit as much as the small holder whose holdings fit up front over here. And I think if you fast forward till today, the experience has been otherwise. It's the small holders who have probably benefited or used the technology the most. Earlier, I mentioned that there are about 17 million farmers around the world that use GMO technology. About 16 million of those, almost about 90% of those, are classified as smallholders, 2.5 hectares or less. So why would smallholders be investing in this? It's profitable. It makes life easier for them. Overall, there's a firm, there's an accounting firm in London that has kept track of investments and profits in agriculture for many years. And since they started keeping records in '96, they estimate that those farmers who have planted GMO crops have, in general, made about $100 billion that they would not have had otherwise. And if you break it out by country, the earlier the countries have started using it, and the more they started using it, the more the profits have been. About half of those profits are because they have higher yields, and about half of those profits are coming from lower costs. But the U.S. has done so well, almost over $43 billion. And then, you know, Argentina, one of the pioneers, is pushing up 14. China is almost at the same rate. You know, India is a little bit behind. And then the smaller, you know, Brazil started very late. But Brazil's catching up fast, and I think it's going to overtake just about everybody. Philippines are about $264 million. I think it's just reflecting the size of the corn crop here. But again, in China, India, Burma, Pakistan, Burkina Faso, South Africa, Paraguay, these are primarily smallholder farmers. So the data for 2011, which is the last one that's out, is that there was about a $20 billion farm value that came just from the GMO crops planted. There was more expenses, about $5 billion were spent on seed, but that still left $14 billion profits up to distribute among those 17 million farmers. And of that, about half went to developing countries, half went to industrialized countries. And now, because the growth of the GM agriculture is faster in developing countries, this ratio is going to keep on changing in favor of developing countries. Here are just some data. I was in Africa a week ago. Burkina Faso, they have 230,000 hectares of cotton, which is almost 60% of their crop. And those that plant the cotton have about an 18% yield gain. They're saving about $52 a hectare by not having to buy as many insecticides, but they're spending more on the seed, $53. So that they're having to spend an extra $1 a hectare to switch from conventional to GM cotton. But then you have to consider this 18% yield gain and higher quality. That turns out to about $200 a hectare in extra income. And that's one of the extreme cases. Here's a study out of Germany, just published about a month ago, looking at quality of life in the Indian countryside. They were looking at food intake, calorie intake, and it was correlated directly with the amount of GM cotton that the farmers were planting. Again, it's all done by hand. You know, again, small farmers. In general, for every hectare of GM cotton they had, the family had about 50,000 extra calories, and of that, about half was what they were calling the quality calories, that they were able to afford to buy the fruits and vegetables that make for a better diet. Economic data, again, here's some of areas more like the Philippines. I have not been given any economic data from the Philippines yet. But in Honduras, the bottom line is actually this one. For the smallholders, every dollar they put into a GM corn is returning about $5. And it's not always just about the money. I was actually talking with some of the farmers there, and there was one area that caught my attention. He had a small holding of corn, and he just could not make ends meet. He was not getting enough off his holding to feed the family, so he got a half-time job in the city. Working half-time in the city, he had less time to spend on his farm. So things were just getting worse on the farm until he managed to switch to GMC. Particularly the herbicide tolerance. His labor requirements on the farm went down so much that then he could still work half-time and get good yield from the farm, have time to spend with his family, and with the extra money, he sent his kids to private school. So, Colombians have actually done a very extensive and intensive study of the income. And sort of the bottom line is that, the land races have the cheapest seed, the GM hybrids have the most expensive seed. Again, the land races have very low yields, about ton and a half per hectare, whereas the 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 GM hybrids with a moderate management can get 6 tons per hybrid, and per hectare. Income, the thing to notice with the income is the variability there, but the net bottom line is it's hard to make a consistent profit with land raises. And look at the plus or minus here. As your yields go up and your variability goes down with the conventional hybrids, the profits are highest with the GM, and the variability, there's more certainty, is greatest with the GM as well. So again, it starts to explain why it's growing so fast, particularly among smallholders. What about environment? A lot of the environmental impacts are talked about in kilos of chemicals, which is a really bad measure. I have an example that I give. That I can drop a kilo of salt, and you have a kilo of salt in the carpet. I could drop a kilo of cyanide, and the effects would be very, very different. Because kilo for kilo, chemicals are not created equal. So the Cornell University came up with a concept called environmental impact quotient. And for every individual chemical, they factor in the impact on wildlife, how long it stays in the soil, how much of it runs off into the waterways, the impact on the person spraying it, and so forth. And they wrap all that up into one quotient and multiply it by the amount used, and you get environmental impact quotient. So this would be just looking at the impact for herbicide tolerant crops. The simple switching there, they range from as little as about 3-4% for herbicide tolerant beet to as much as about 25% for herbicide tolerant canola, just by one switch. And this does not factor in the impacts of the no-till agriculture and so forth. But insect resistance is even more spectacular. About 25% less impact in cotton and about 40% less impact for corn production. Easy way. So one of the things we have been doing is setting up demonstration plots. We grow the conventional and the GM side by side, and we have field days. And we bring in journalists, and we bring in actually regulators, every now and then a legislator. But you send them out in teams through both plots and look for diversity. And anything that's been conventionally sprayed, you're not going to find much in it. But then you find just so many different things in your GM plots where you're not using as much the traditional pesticides. And we have a lot of data. Where I live, it's a big cotton growing area. The birds are back. We're not killing the birds with the insecticides as we were before. They hear data from Australia. This happens to be drinking water. This was their cotton growing area. The white line is what the government considered to be a safe level. And it wasn't until they started planting GM cotton that drinking water truly became safe. But overall, we get back to the original premise. I mentioned that farmers like to harvest yield, not other diseases. Diseases decrease yield. Here's a good example. This is an engineered potato, non-engineered potato. And at harvest time, you can see the amount from here and the amount from there. And it's when you start looking at photographs like this that you start to realize how much yield is lost on a global basis. In fact, of the 5 major crops, which is corn, cotton, soybean, wheat, and potatoes, somewhere between 20 and 30% of yield is lost every year to pests and diseases. So sometimes simply stopping losses would go a huge way towards meeting our food supply demands now and in the future. And if you look at some of the data on the countries that have, this is just yield increases by preventing losses. With cotton, India has done very well, 40% greater yield, Argentina 30, South Africa about 25. If you look at corn yields, Colombian corn yields increased about 20%, Philippines have increased about 18%, and so forth. And if you compare it then with countries like the US and Canada was up here, their increases have not been so high. They're in more of a pest-free environment, and they had better control measures to begin with. So again, the tougher environments are the ones that tend to get the greatest yield gains. And then we also come to a point where not only do we lose yield from pre-harvest, we have post-harvest losses. And that's a big area of growth. In this case, we have 2 potatoes that were sliced at the same time and apples that were sliced at the same time. And you can see the oxidation that's taking place and making them unappealing. So again, if you can start preventing post-harvest losses, we, again, help contribute towards meeting the necessary food supplies of the future. So, of all the stuff that's out there, it hasn't just, I haven't made a plant and just shipped it out and planted it. It's gone through 2 safety assessments, and I could actually give a whole day seminar on environmental safety assessment, and I could spend 2 days on food safety assessment. Suffice it to say that there's a criterion that there will not be any novel risks. Agriculture is not risk-free. And agriculture has caused a lot of environmental damage. It's promoted erosion, it's promoted pesticide abuse, and whatnot. So the idea is to not add to the list of damages agriculture does, and if we do things well, we actually remove some of the damage that conventional agriculture has done. So we have to ensure there will not be new risks to agriculture, or that includes wildlife. Many times, our goal is to kill a corn earworm. We don't want to kill the earthworms and the birds and butterflies and everything else. And we need to make sure there's not going to be gene flow that will cause problems. Gene flow has always existed, will always exist. We just need to make sure we're not going to add something that's going to cause a problem. And that's regional in nature. So this is done, gene by gene, crop by crop, location by location. So whereas this is regional, food safety is universal. The criterion is that a food from genetic engineering has to be as safe as conventional food. So if people ask me, can you guarantee it's safe? I can always guarantee that it is as safe as what you're already eating. I can't guarantee that what you're already eating is completely safe, but I can guarantee that it'll be as safe as the GM version. And it's global. If it's been tested in the European Union or China or wherever, and if they haven't found problems, it's going to be safe around the world. You can always look at regional differences in consumption, but in general, it's considered safe. So, in the global market that we have today, where anything that's planted anywhere can end up just about anywhere, the practice is, at least for the major importing countries, that if I have an engineered plant that's going to go out, the major importing countries, actually a lot of countries will test the safety. It's a pretty long list, but probably the major importing countries are here. They do their independent testing and they do their independent assessment. So the Chinese Ministry of Ag, Health Canada, the Food Drug Administration of the US, the food standards for Australia, Korean FDA, Japanese Food Safety Commission, European Food Safety Agency. The toughest 2 have been Korean and Japan. But it's only until the major countries have decided it's safe that this reaches the global market. So the point of the matter is there's just a lot of redundancy and multiple layers in the system. The amount of data that is required to meet its requirements, it takes about 34 million US dollars to get. And it's excessive. And we're really going to be creating crops for smallholders and whatnot. The number has to come down. I'm convinced with modern technology, we can get this number way down without compromising any safety at all. So, there's not been enough studies done. There's been a ton of studies done. There's 3 websites here, and they have compiled a list of all the refereed literature on GMO food safety testing. And they've been communicating with each other, so they have the same list. But this one's in Australia, this one's in Chile, and this one is in the US. But I think one of the most convincing reports is this one's from the European Commission, and anyone can now download the report and read it for themselves. It's called A Decade of European Union-Funded GMO Research. And in it, it says that the main conclusion to be drawn from 130 studies, more than 25 years of research, and 500 independent research groups is that biotechnology, and in particular GMOs, are not as such more risky than, say, conventional plant breeding technologies. So they also conclude it's as safe as conventional food. I'm going to specify a little bit about nutritionally enhanced crops. This one is the one being developed in the Philippines. It's the most advanced. It's golden because of the beta carotene that people need to for vision, vitamin A. But if you're in Africa, the work is being done in bananas. If you're in South America, it's being done in potatoes. It's portable technology. You can look at a map. This is World Health Organization. And in that map, you know, red means critical. And this dark orange means almost critical. Why? It's of all the nutrients, it's the most limiting nutrient in the world, and it's primarily a tropical problem. Now, I can show you guys a map, and you know, it's just a map. Or I can show you a photograph of what it means to be vitamin A deficient. It's a girl, she's from Bangladesh, she's blind. And she's blind for one reason only: lack of enough vitamin A in her diet. And just like her, there's another 500,000 children that are permanently blinded by vitamin A. And it doesn't stop there. If you're vitamin A deficient, you're predisposed to a lot of other diseases. And if you're predisposed to other diseases, it ends up an additional 2 million deaths a year. These numbers come from WHO. And we can do something about it. So, with the recent destruction of rice that took place here in the Philippines, you know, the center of development is in here. It attracted global attention as it had never attracted it before. Actually, golden rice got more positive press out of that one act of vandalism than it had up until now. And it started out with this petition that in less than 24 hours had gotten over 1,000 signatures from the most prominent plant scientists around. And it just took 48 hours to come up to 4,000 signatures. And it's still there at 6,000 signatures. At this point, there's not a whole lot more plant scientists left on Earth that can still sign it. And you know, it even gave an editorial in the New York Times. And you know, normally they give very negative press, or if they pay attention at all. And then in the last week, the issue of Science, the editorial standing up for GMOs, was written by the most prominent plant scientists around, including 2 Nobel laureates. So the global spotlight is now on the Philippines to see what's going to happen with the golden rice here. And you can expect a lot more publicity on it. So to finish off, my take-home message is, genetic modification is not new. We've been doing it for really thousands of years. We just didn't know what we were doing back then. As far as traits go, there's the soybean being made. Here's the list. Right now we're working on, we have drought, disease tolerance, insects, herbicides, nutritional enrichment. And as time goes on, we hope to have a lot more there. But technology has been too popular with farmers. It's here to stay. We can't get rid of it at this point. So it has to be looked at as part of a solution to meet the challenges. We have climate change coming on. We have population that's going to keep on. We have a couple more billion people are going to be added to the problem. We're better off if we consider part of a way to solve a problem, not a problem to be solved. Safety. Of all the problems that people were afraid of 20 years ago, 17 years later, with the billion hectares, 30 countries, 17 million farmers, they simply have not materialized. As I mentioned, there's extensive safety testing that goes on around the world. They're most studied foods in history. And there's always negative claims. And there will always be negative claims. What we're waiting for is a negative claim that somebody can actually confirm. Right now, none of the negative claims have been credible for a variety of reasons. So we can really say that they are as safe as conventional food. However, as I said at the beginning, distribution is still limited. Most countries people there have never seen a GMO crop. They've only seen what's on the internet. They don't know what a GMO crop really is. And in a background like that one, it's very easy for misinformation to circulate. And our challenge is dealing with that misinformation for the time to come. So with that picture from my home country, and wanted to thank you very much for your attention.